All right. Good afternoon, everyone. Welcome to the International Methods Colloquium. My name is Justin Essery. I'm an associate professor of politics and international affairs at Wake Forest University. The IMC is a periodic, online, interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Wake Forest University and co-sponsored by Springer Publishing. This week's speaker is Nicole Pashley of the Department of Statistics at Rutgers University. Her talk is entitled Noncompliance and Instrumental Variables for 2 to the k factorial experiments. And as you can see from the slide, it's joint work with Matt Blackwell of Harvard. Nicole's talk is going to last between 30 to 40 minutes, for which point we will take questions from the audience. You can ask a question using the Zoom Q&A button at the bottom of your webinar window. And you can ask a question at any time, but we will hold all of those questions until the end of the presentation. If you wish to be recognized and ask your question via audio, please indicate this in the Q&A text box, and we will, when the time comes, recognize you. You can unmute yourself and ask your question. Otherwise, I will read your question during the Q&A period. A link to Nicole's paper and slides will be available in the Zoom webinar chat window so that you may refer to it throughout the presentation. And I will post those links right after this introduction. Now I'd like to welcome Nicole Pashley to the International Methods Colloquium. Welcome.
Thank you very much. I'm excited to be here and talking about noncompliance in factorial experiments. So as Justin said, this is joint work with Matt Blackwell, who's at Harvard University. So in the social sciences and many other fields, we're often interested in the effect of multiple treatments on some outcome, and we're interested in how those treatments may also interact with one another. Luckily, we know what to do in these situations, right? We should run in a factorial experiment where we randomly assign multiple factors at the same time to individuals in our study. We can use these experiments to then estimate marginal, joint, and interactive effects of these multiple factors of interest. We also often have noncompliance in social science experiments, right? People don't do what we tell them to do all the time. So for instance, in get out the vote phone call experiments, there's a compliance rate of about 20%. So that's about 20% of people actually picking up the phone and talking to the person who's calling. And so we know what to do with noncompliance when we have a single binary treatment. We can use the instrumental variables approach. But we don't know what to do with the combination of these two problems, multiple treatments and some noncompliance. So almost all analyses of factorial designs assume perfect compliance, but it feels like we should be able to do something better here, right? We should be able to take into account that noncompliance. And so that's where our work comes in. So in our paper, which I'm talking about today, we set up a framework for 2 to the k factorial experiments with noncompliance. We generalize IV assumptions and estimands to the factorial setting. We define what it means to be a complier in the setting, and we talk about how to conduct finite sample and Bayesian inference here. And so this work generalizes and extends some previous work by Matt on the 2-by-2 special case and get out the vote studies. For today, I'm going to be just focusing on kind of randomization-based finite sample inference. But if you're interested in more, and if you're interested in a more detailed and a lot of math and notation on this work, please do check out our paper. All right. So to make things a little bit more concrete, we're going to go through an application setting at the end, and I'll refer to it as an example throughout the talk. So there's this study by Blattman, Jameson, and Sheridan looking to reduce violent and criminal behavior in young men. And they ran a factorial design with 2 factors, cash transfers and cognitive behavioral therapy. So there's a little asterisk next to factorial designs. Technically, the experiment they run wasn't exactly a factorial, as we'll define it later, because they did independent assignment of these 2 treatments, these 2 factors. But using conditioning, we can basically analyze it as a factorial design without any problem. So they had 999 young men in Liberia who were had a history of previous violence or criminal behavior. And they collected a variety of outcomes having to do with economic outcomes, antisocial behavior, and quality of social network. And they collected these outcomes at the short term and at the long term. And so perhaps not surprisingly, for the cash treatment, they didn't have a lot of noncompliance. Only 2% of the people who were offered cash didn't take it. It's almost surprising that 2% of people did not take the cash. But for CBT, about 37% did not complete the cognitive behavioral therapy that they were assigned to. So we have another application in our paper, this 2 to the 3 get out the vote field experiment. So if you're interested in that, do check out our paper. So before I jump into sort of our contributions and what we're doing, I just want to do a quick refresh on what's a factorial design and what are we doing in the standard IV setting with a single binary treatment. So in a 2 to the k factorial experiment, we have k factors that we're interested in, and each of these factors has 2 levels. And we usually label the levels as +1, which could be, for instance, treatment, and -1, which could be control. So this is a little bit different, the +1 and the -1, than the kind of usual 1-0 notation in potential outcome, causal inference world. But this is sort of the usual notation in the experimental design literature. So as an example, in the application I just introduced, cache was one of the factors, and it had these 2 levels. You receive the cache or you don't, +1, -1. Similarly for the factor of therapy. One treatment for an individual is then a combination of the levels of these k factors. So for instance, one treatment for this example is you receive the cache but not the therapy. And there are a total of 2 to the k possible treatments with k factors. So in this example, we have a 2 to the 2, which equals 4. So we have 4 possible treatment combinations in our example. Treatments which are combinations. And so the actual design, how we randomize people, we use complete randomization. So we randomly assign a fixed number of units to each of these possible treatment combinations. So for instance, if we have a design and this is our group of people, and if it's just a 2 by 2, we have these 4 treatment combinations, which are defined by the levels of the 2 factors. And we randomly assign a fixed number of people to each of those buckets, each of those combinations. So for this illustration, I did a balanced design where I have an equal number of people assigned to each combination, but it doesn't have to be. This allows for unbalanced designs where we have unequal proportions of people in each treatment group. That's totally fine. Now, what about IV with a single factor? Just as a quick review, in the IV setting, we have a binary treatment, the usual IV setting, we have a binary single treatment ZI, but we have treatment uptake DI, which might not equal ZI. In other words, some people in our experiment aren't doing what we told them to do. They're not taking the treatment we assigned. And what I really want to understand is the effect of DI on YI, not the effect of, the effect of the actual treatment they actually took. But the problem is there might be confounding, right? Because we didn't actually randomize D, we randomized Z. We just observed D. And so we can define these potential outcomes. First, you have a potential outcome for treatment uptake depending on your assignment of Z. So you have, in this case, 1 treatment uptake if you were assigned to treatment and 1 if you were assigned to control. And then we have the potential outcomes for the outcomes themselves, which are a function of the treatment that you were assigned and the treatment you actually took, so Z and D. And once we've defined these, we can define or group our units or stratify our units into these principal strata, which are defined based on their pair of treatment uptake potential outcomes. So we break them into the groups compliers, always takers, never takers, and defiers, where hopefully the names are pretty self-explanatory. Compliers do what they're told. Defiers, on the other hand, will do the opposite of what they're told. So if you assign them treatment, they'll take control. If you assign them control, they'll take treatment. And of course, we can't categorize everyone from the data into these groups using our observed data alone, because for instance, for when assigned to treatment, the compliers and the always takers behave the same. They both take treatment when assigned to treatment. And so what do? We define these IV estimands, which are these ratios of intent to treat effects. And so this tau is the ratio of the intent to treat effect of the treatment assignment on the outcome to the intent to treat of the treatment assignment on the treatment uptake. And then there's these classic IV assumptions that allow us to interpret this estimand in a reasonable way. So random assignment of treatment, the exclusion restriction. The exclusion restriction says that the effect of treatment assignment is only through treatment uptake. So as long as you hold an individual's treatment uptake constant, their assignment doesn't actually matter. In other words, there's no arrow from Z to Y directly. And then we also have this monotonicity assumption, which rules out defiers. So we can't have those people who just rebel and do the opposite of what you tell them to do. And then we also need this basically non-zero effect of Z on D, that there's some compliers in our experiment. And there we go. If we can do that, then we can interpret, if we can make all of those assumptions, we can interpret this tau, this ratio estimand, as a local average treatment effect, where it's local because it's the average treatment effect specifically for the compliers in our experiment. And so that's going to get us an estimate of it's an estimand for the effect of D on Y, because the compliers are the individuals where their treatment assignment actually equals their treatment uptake. So even though we have this possible confounding between D and Y, we can still back out a reasonable estimand for those individuals and an estimator for this estimand for those individuals who actually do comply with treatment. All right, so what about our setting? So we have a 2 to the k factorial experiment. Again, k binary factors with levels -1, +1. We then have these treatment assignments, ZL, which are going to be vectors of treatment assignments, where each entry in the vector corresponds to the assignment for a particular factor, 1 through capital K. And so for instance, for the 2 to the 2 case, we have these 4 treatment assignments. And for instance, the first treatment assignment has level -1 for both factors, so control for both factors. And the fourth assignment in this table has +1 for both factors, so assigned to treatment for both factors. Because we're considering the case with non-compliance, we also need to define this treatment uptake vector, DL. DL is going to, again, be really similar to the ZL in that it's going to have an entry for each factor in our experiment. So it's just giving the treatment uptake for each of the factors that you have in the experiment. And each of these vectors has 2 to the k possible values because for each entry, it can take one of 2 values, -1 or +1. And then just like in the binary IV case, we can define a potential treatment uptake. And so this is going to now just be a vector of treatment uptake that depends upon which assignment the individual was given, which treatment assignment. And so again, non-compliance means that your uptake vector doesn't equal your treatment assignment vector, at least for some units in the study. And we can also use this notation DI with the little k subscript to give treatment uptake for specifically to grab off the treatment uptake for factor K given assignment to factor Z. So this just pulls off what level of did you take for factor K specifically. Then our potential outcomes for treatment assignment and uptake are, YI, which depends on Z, and D, the treatment assignment vector and the treatment uptake vector. Now, because treatment uptake depends entirely on your treatment assignment, we have one treatment uptake for each assignment for each individual. We can just write these Ys as a function of Z and leave the dependence on D implicit through its function of Z. So of course, we need to make some assumptions in this case as well to move forward. So we assume that Zi is completely randomized, right, using that factorial design. We assume monotonicity, and this looks like the monotonicity we see in the binary case, and it is similar. But now it's kind of got this conditional nature to it. So this is the assignment uptake for factor K. Right, and what I'm doing is I'm changing the level of factor K from +1 to -1, but keeping the assignment of the other factors the same. So this is like saying conditional on the assignment of the other factors, you can't be a defier for a given factor. And that's going to have to hold for all assignments of the other factors. Then we have this outcome exclusion restriction. This looks really the same as before and just says that treatment assignment only affects outcome through treatment uptake. There's no other path. And if I just had these assumptions, I would actually have way too many compliance types. Because here, remember, we have this multidimensional treatment assignment vector. And so for each factor, we'd have to ask, are they a complier conditional on the assignment of the other factors? And so for each assignment of the other factors, you could be a complier, an always taker, or never taker, because we've ruled out defiers. And there's 2 to the k minus 1 assignments of those other factors. And so we just, for each factor, you have this crazy number of possible compliance statuses. And then to describe a person's compliance in total, you have to combine all of the compliance statuses for all the factors. And it's way too many compliance types to actually deal with. And so we're going to have to add on another assumption to make this problem feasible. And so we use the treatment exclusion restriction, which was originally introduced in Matt's earlier paper, where we assume that the compliance, or sorry, not the compliance, but the treatment uptake on factor K, given assignment Z, only depends upon the treatment assignment to factor K in that assignment vector. So in other words, in the 2 by 2 case, your uptake for factor 1 only depends upon the assignment you got for factor 1. It doesn't matter what you were assigned to factor 2. It only matters what you got assigned to for factor 1. So there's no effect of the other treatments on your treatment uptake. In other words, in this little picture, we've ruled out the arrows from Z1 to D2 and Z2 to D1. There can be no kind of cross impacts. And we fully admit that this is not going to be plausible in all settings. Just like outcome exclusion restriction is not going to make sense in all settings, this might be too strong to be realistic in some cases. But we need to do something to make this problem feasible, and we think that this is a good start. It's interpretable, it's easy to understand, it's easy to think through logically whether you think it could hold or not in your setting, and it has some testable implications. So this is what we're gonna use today. And we are thinking about ways to kind of try and weaken this to allow for sort of more general settings of inference. All right. Oh, I just lost my slides. There we go. Okay. So once we have this treatment exclusion, and we also have monotonicity, as I just defined them, we can now categorize each unit into one of 3 to the k possible compliance types. And so we can let Ti be this vector of compliance types where each entry is the compliance for each factor. So for instance, for factor K, you can be a complier, an always taker, or a never taker on that factor. And remember that it only depends, your treatment uptake only depends on what you were assigned to that factor, okay? And so this is gonna be a much more manageable problem of trying to figure out what's going on with 3 to the k compliance types. So treatment exclusion is really important here to make the problem feasible. Okay, that's our setup. Those are our assumptions that we're going to need. So what are we actually trying to estimate here? So in the binary case, we saw that our IV estimand was this ratio of ITTs, right? So it was the ITT of Z on Y to the ITT of Z on D. And so how do we write this or generalize this to factorial designs? And so we're going to use the factorial effects framework from this paper by Dasgupta, Pillai, and Rubin in 2015. And we've been using that notation actually up until this point as well. So we have these 2 to the k potential outcomes for each unit. And we're just going to collect those into a vector, yi dot. So for instance, for the 2 to the 2 example, we have these 4 potential outcomes for each individual, and we just collect those into one vector. And then we can define the ITT effects by using these contrast vectors, these GJs. These GJs are vectors where half the entries are +1, half are -1. And we basically have one contrast vector for each effect. So the first k of them correspond to main effects, and then the next k choose 2 contrast vectors will correspond to two-way interactions, and so on to all the way to the k-way interaction. And we can use these then to define our causal effects in this really compact way, using this vector multiplication. And I know this looks like a lot, and so let's just break that down a little bit by going through an example in the 2x2 case. So this is what my science table, if you will, looks like for the 2x2 case. We have all of our treatment assignments, and then we have the true potential outcomes for the given individual under each of these assignments. And so for the main effects, the G vectors are just these columns corresponding to the levels of that factor for each of the different assignments. So G1 is the contrast vector we're going to use for the main effect of factor 1. And that's just, each entry is just the level that factor is assigned to for each of these different treatment assignments. Similarly, for factor 2, it's just the levels of factor 2 for each of the different treatment assignments. That's what our G2 is. To get the interaction, what we're going to do is we're going to do an element-wise product of these two columns. So for instance, -1 times -1 is +1. So I'm just doing element-wise row by row multiplication of each of the entries to get my interaction vector, taking the Hadamard product of G1 and G2, and that gives me G3, right? So that's my two-way interaction is going to be G3, the interaction between factor 1 and factor 2. Okay, so that's how we define the G1s and the G2s and the G3s. You'll notice again, half our entries are +1, half are -1. So how does that work out into helping us define estimands? So let's just rewrite that table with the G's up here and just cutting out a little bit of the extra stuff we don't need. And so I said, our estimand is defined as do the vector product of G1 with the vector of potential outcomes. And so that's going to give us this as our estimand. And what you'll notice is that this has two parts. The first part for this 2 to the 2 example is the effect of factor 1 when factor 2 is at +1 level, right? We're changing factor 1, but keeping factor 2 at the +1 level. And this second piece is the effect of factor 1 when factor 2 is then at the -1 level. So what's the effect of changing factor 1 while holding factor 2 at the -1 level? We multiply by 1/2 in this case, and we're adding them. So what we're doing is we're taking the average effect of factor 1, where we're averaging or marginalizing over the levels of factor 2. And so we can do the same thing for factor 2, right? Multiply the G2 vector by the vector of potential outcomes, and we again get this piece corresponding to factor 2 when factor 1's at the high level versus factor 2 when factor 1's at the low level. For interactions, mechanically, it's the same thing to get the estimand, right? We multiply the given vector by the vector of potential outcomes. And what I get is something that looks kind of like the first estimand. I can write this as the effect of factor 1 when factor 2 is at the high level versus the effect of factor 1 when factor 2 is at the low level. But now I have this minus sign. So the interaction, it's like the interaction in a regression, is the difference in effect of factor 1 when factor 2 is at the high level versus the effect when factor 2 is at the low level. So it's this kind of difference in differences interpretation. Okay, so that's how we think about our main effects, right? The effect of the factor averaging over the levels of the other factor. We can define them using those G vectors. And so then we can take the average of the potential outcome vector averaging over all individuals in our study to define our finite sample average ITT factorial effects. In other words, the estimands for all individuals in our study, right? Define them the same way, just now with that mean vector. And again, the main effects we're thinking of the effect of the factor marginalizing over the levels of the other factors. For interactions, it's going to be the interaction between two factors. And we didn't really see this in the 2x2 case, but in higher, with larger K, you'll see that the interaction is the interaction between the given factors averaging over the levels of the factors not included in that interaction. And so if you're familiar with the conjoint design literature, these are very similar to the average marginal component effects in that literature. And again, these are sample estimates. We're not assuming some kind of larger population. These are estimates for the units actually in our experiment. So those give us our ITTs intended to treat for outcome of the assignment to outcome. Those gives us our estimands. But what about for treatment uptake? And so we can think about how we defined the ITTs for the outcome and try and translate that over to the treatment uptake. So we can define this vector DIK, which is the vector of your treatment uptake for factor K for each assignment vector Z, right? So this is just like our vector of Ys, it's just now using the Ds instead of the Ys. So what treatment you take for factor K, what level you take for factor K for each of the different treatment assignments. And we can use this vector and basically just stick it in that formula we used before, replacing the Y with the D, to get a ITT of treatment on uptake for factor 1. So we can just define that like this. It's a little bit more complicated to define for interaction, so I'm going to introduce some new notation to make this work a little bit better for the more general case of factorial effects. So when I defined the factorial effects for the intent to treat on outcomes, we had these 2 to the k minus 1 basically effects we're going to end up with, where the jth effect was the effect for some factor or some set of factors. And so we're going to call the factors involved in that effect the active factors. So for j equals 1, this was the main effect of factor 1. So we would say the active factor was just 1. For j equals 3, in that 2 by 2 case, that was the interaction between factor 1 and 2. So we're going to say the active factors there are factors 1 and 2. Then we can define this d tilde as the element-wise product of uptake between active factors of the jth factorial effect. So for effects where there's just one factor, for instance, for the first, j equals 1, this d tilde is just equal to the treatment uptake vector I defined on the last slide. So just your uptake for each assignment. But for these interaction effects, we have to do a product. And this is again going to be like this element-wise product for each element in the 2 vectors between the uptake vectors for the factors involved in that interaction. So this is going to look a lot like how we define G3 using G1 and G2. So we're doing the same kind of thing now with these D vectors, these treatment uptake vectors. And once we define these D tildes, this way it's really easy to define our ITT estimands as basically the factorial effects on these D tildes, where you just need to make sure you're matching the D tilde up with the right G. And so the first one is going to be the effect of treatment, the main effect of treatment for treatment assignment of factor 1 on treatment uptake for factor 1. And the second one is going to be the interaction of assignment for factor 1 and factor 2 on the joint uptake, or the uptake multiplied together of factor 1 and factor 2. So that's going to be our interaction effect. Okay. So then we can define IV ratio estimands as the ratio of these 2 sorts of ITT effects we defined. So the jth factorial IV estimand of this type is going to be a ratio of the jth factorial ITT effect on Y. So for instance, it might be the main effect of factor 1 on outcome over the jth ITT effect on the D tilde J. So that could be the effect of assignment to factor 1 on uptake of factor 1. So without the IV assumptions, this is always something we can just interpret as the ratio of 2 ITT effects. But with the factorial IV assumptions, we get something much cleaner, because delta bar J is going to actually be the proportion of compliers portion of individuals who comply with the active factors in effect J. So for the J equals 1, we're talking about factor 1. This is going to be the proportion of individuals who comply with assignment to factor 1. When we're talking about J equals 3, that interaction between factor 1 and 2, this is going to be the proportion of individuals who comply on factor 1 and factor 2. And so then this ratio is going to be the marginalized, what we call the marginalized complier average factorial effect, or MCAF. And so this is going to be the marginal factorial effect of, for instance, factor 1 on individuals who comply with factor 1. The effect among compliers who comply on the active factors in that factorial effect. And we also need to assume delta bar J not equal to 0 here to make this well defined. So we now have this marginalized complier average effect, marginalizing basically over the levels and also the uptakes of the other factor, where we're just looking at individuals who comply with the specific factor that we're looking at in this estimand. So the problem with this is that the conditioning set changes across factorial effects, right? Because these are local average treatment effects. They're defined for specific subpopulation of our experimental unit population. And so, for instance, for the first factor, you're looking at people who comply on factor 1. And for the second factor, you're looking at people who comply on factor 2. And these might be two totally different subsets of people. And so it makes it difficult to compare relative sizes of main effects and interactions, because you're not really comparing apples to apples, because you're comparing different effects and different people. And so, for instance, if I had a 2 to the 3 design, so now 3 factors, and I was looking at the interaction between factor 1 and 2, the marginalized compliers that I'm averaging over are basically anybody who complies on factor 1 and factor 2, but could be doing anything else on factor 3, complier or non-complier. And so we propose an alternative to make these effects more comparable, which is to look at what we call perfect compliers. So the people who comply on all of the factors in the experiment, who always comply with everything. And once we do that subset to that group, we can compare all these effects with ease and make it a little bit more interpretable. And so we're going to denote these as gammas in our paper. So that's the jth perfect complier average factorial effect. So we basically do those estimates I just showed, but now define them just for this subgroup of perfect compliers. And it's going to end up being a ratio of effects, just like we saw. It's just a little bit more complicated, so it's not something I'm going to cover today. So there's our estimands, our assumptions, and everything. How do we do inference? So of course, each person is actually assigned to some treatment. And so we get their indicator of whether they, what treatment they were assigned to, whether they were assigned to the L treatment combination or not. We have NL units assigned to each treatment combination that's fixed ahead of time. And so then we can define the observed average outcome for units who are actually assigned to ZL as the average over the people who are actually assigned to ZL, right? And so we can make our estimators, our ITT effect estimators, by just replacing Y bar with Y hat in those expressions. So that's exactly what's happening here. This is that main intent to treat main effect of factor 1 on outcome, where I've just replaced the Y bars with Y hats. So this is just my estimator, my observed effect. And similarly, you can do the same thing for the treatment uptake ITTs, the delta hats, by just replacing the Y's with the D's, put in the observed treatment uptake means for each assignment. By randomization, these are just linear combinations of means. So the ITT effects tau hat J and delta hat J will be unbiased for their true ITT estimands. And then we have this ratio estimator, which is the ratio of these two ITT effects. And so to do inference for that, we focus on finite sample inference. So potential outcomes are fixed. Randomization is only coming from random assignment of treatment. We don't think about the data generating process for the outcome at all. And we use finite population central limit theorems, which allow us to test weak nulls, think about means, not sharp nulls. The distribution of these ITT estimators then are approximately normal as our experiment, the size of our experiment grows. So there's two ways to then specifically conduct inference for a ratio in this setting. One is to use the delta method. You can use a finite population version of the delta method to get the asymptotic distribution of this ratio estimator, which gives you the asymptotic variance, which you can then create an estimator for and create confidence intervals as usual. The issue is that this is going to have poor behavior when it's going to be pretty unstable when compliance is very low, the denominator is close to 0. So instead we can use this trick, Feiler's method, which basically inverts a test statistic, and it creates confidence intervals that have really good coverage, even when compliance is low. The only drawback is that they can also have infinite length, which is obviously pretty uninformative, but perhaps tells us that we don't have a lot of information in our data in that setting. So if you're interested in a more thorough treatment of these, do check out our paper. So just to quickly go over the application to see how our new estimators are working out. So remember, we had this 2 factors, cash and cognitive behavioral therapy. And people who were assigned to cash, this is in the setting one-sided noncompliance. But the people who were assigned to cash were generally taking the cash, so compliance was high for that condition. But for CBT, it was much lower at 63% of people being assigned to CBT actually followed through. And we're defining compliance for this example as attending 80% of the meetings. And so the perfect compliers were very similar to the compliers for CBT because basically everybody's complying on cash. So when we look at those estimates, we're expecting the PCAFs and the MCAFs to look very similar for CBT, but we might see differences in the cash treatment. And so that's exactly what we see. On this graph, we're looking at 3 different estimators, ITT, just the ITT on the outcome, these MCAFs we defined, and then the PCAFs. We're looking at 2 outcomes, short-term social networks, long-term social networks, and then we're comparing across the different factorial effects for cash, CBT, and the error interaction. And what we see is that, as we said for CBT, the marginal complier effect and the perfect complier effect are looking really similar. But for cash, we see actually a difference between the marginal complier effect and the perfect complier effect, because again, for the cash, almost everybody's complying to cash, but not to CBT. So the perfect complier will look different. And we actually see that it makes a difference in our conclusions here because the PCAF is not significant. Of course, for perfect compliers, you have a much smaller subset of the data, and so we expect larger confidence intervals there to result. And so for cash also, you'll notice that they look more like the ITT estimates because almost everybody's applying to the complying with the cash condition. Okay. So in this talk, we talked about trying to address these 2 issues we have in social sciences often at the same time, multiple factors and noncompliance on at least one of these factors. So in our paper, we've built a framework to handle these. We've generalized the IV assumptions and estimates to the factorial setting. We talk about different types of compliers, these marginalized compliers and these perfect compliers. We've created consistent estimators for these complier effects. We discuss confidence interval procedures and other inference procedures in detail in our paper and lay out exactly how to do that and how to generalize the binary methods to the factorial setting. And we also have an R package, which is really all thanks to Matt, where you can implement our methods if you're interested. And so in the future, we're thinking about things like weakening the treatment exclusion restriction, perhaps doing a bounds analysis instead, because it is pretty strong assumption, allowing for more than 2 factors per our true levels per factor, using covariates to characterize our marginal compliers, and thinking about how to handle multiple comparisons in this setting, as obviously you're comparing a lot of different things. So I know I just talked a lot. Thank you so much for sitting through it. Our websites are here, and please do check out our paper if you're interested. We'd love to hear thoughts. Thank you so much.
Okay. Thank you, Nicole, for that presentation. At this point, Nicole Pashley is available to take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. If you wish to be recognized and ask your question via audio, please indicate this in the Q&A text box. Otherwise, I will just read your question. And we already had one question come in from Thomas Ball, so I'll just go ahead and ask that question right now. Thomas asks to please elaborate on why relaxing the treatment exclusion assumption results in a, quote, crazy number of factor levels. How big is a crazy number?
Right, so it's not a crazy number of factor levels, it's the number of compliance types gets really big. And so we think that there will be, I guess I should say something first. We think there'll be, oh, sorry about that. Let me see if I can get this back up. There we go. We think there are going to be ways to relax this. We're hoping that there are ways to relax this that reduce the number of compliance types and makes inference, make us be able to go forward in inference. But I'm just saying you need some extra structure because thinking about this problem, let's think about the 2x2 case maybe to make this a little more concrete. For factor 1, I may comply on factor 1 when I'm assigned to factor level 1 of factor 2, but I might not comply. I might be an always taker, for instance, when assigned to level -1 of factor 2. So without this treatment exclusion restriction, I can have all of these conditional versions of compliance for each factor. So each factor, basically, when I think about compliance for a given factor, I have to think about your compliance conditional on the assignment of all of the other factors if I don't have this assumption. And so that means that for each factor, I have, hopefully I've done the calculation correctly, 3 times 2 to the k-1, because there are 2 to the k-1 assignments for the other factors. And for each of those assignments, you can be in one of 3 classifications: complier, always taker, never taker. And so that's just for one factor. When you have look at all k factors to try and classify somebody's compliance status in general, you then have these 3 times 2 to the k-1 possibilities multiplied across your k factors. So it's going to get really big really quickly. And the point is that it's just a little too unwieldy to try and deal with without some additional structure on what type of non-compliance is allowed here.
Well, the alternative would be, I think, to impose a different kind of structure. So, for example, you could impose, some form of data generating process assumptions that hopefully wouldn't be, too restrictive. And I'm kind of curious about which is better, right? Is it better for me to specify some sort of quasi-linear or sort of limited polynomial structure and then hope for the best? Or to impose this set of assumptions?
Yeah, that's a great point. And yeah, we definitely think that's kind of one of the next directions is thinking through different ways to think about assumptions on compliance types. And yeah, whether it's a model or in the paper, we do discuss one relaxation where we kind of restrict the way you're allowed to be a non-complier or the way the factors are allowed to interact to affect treatment uptake when you're a non-complier. But things get really complicated in that case when you start thinking about interactions. Other things we've thought about are, in some cases, you might have, for instance, the factors are basically exchangeable in terms of thinking about compliance, whether you're complying on factor 1 or factor 2, but it might be that being assigned too many, the positive level of too many factors, the treatment level of too many factors might cause somebody to switch from a complier to a not complier. So I think there's a lot of possibilities here in terms of whether using a model-based approach versus our restriction is better. I don't know empirically which is going to be better. I think our goal for this is kind of it's a hopefully somewhat reasonable assumption in some cases, and it's really easy to understand what the implications are and to try and think through, do I think the assignment of factor 1 affects the uptake of factor 2?
I want to, because this is It's not a podcast, is it? A webinar? Seminar series? Whatever we're doing here. This is targeted primarily at applied statisticians, right? People like me who are mostly doing some statistical work, but mostly it's about answering substantive questions. And I think it might be helpful. You did have an example in your presentation, but I think it might be helpful for us to hear about the kind of situation where this approach would be better than what I would say the default approach would be to just sort of marginalize by like, okay, here are the people who are assigned to one treatment. Now I'm going to look at the marginal effect of being assigned to the other treatment conditional on that first assignment. What in a substantive way, what's the advantage of trying to apply your basically to estimate your estimands as opposed to taking a simpler approach?
So I just want to make sure I'm understanding the simpler approach. So are you saying doing just like the ITT of Z on Y versus doing the kind of IV version?
That would be the most simple thing, right? Literally just
Right.
an ITT. But I think one step above that, right, like the sort of seat of your pants methodology would be something like, okay, I've got two treatments. I kind of want to know how much the one of the treatments does better once you've already been assigned to the other treatment. So I just literally subsample the people who are assigned to their z sub I is equal to 1. We fix that constant, and we look at the marginal effect of z sub j by just doing the usual difference in means test, assuming that there's random assignment.
Okay, yeah. So I think that's partly like a difference in estimand, right? It's whether
Yeah.
you're interested in these kind of conditional effects or not.
That what I'm
And
really,
I
I
think,
guess, what I'm really asking you is why is this estimand better, right? Why is this estimand when you're talking to a substantive person? Why would I want to focus on your estimand?
right. So basically, I mean, hopefully it's sort of the reason we want to do IV analysis in the binary case too. We want to address the fact that we know there's noncompliance that's going to be affecting our point estimate. And we want to account for that noncompliance so that we're actually estimating the effect of taking treatment and not just assigning treatment, right? Because that's usually, I think, substantively what we're interested in. And so that's really the goal of this. And so once we take out those noisy noncompliers, you're hoping that you're getting better inference for the things you care about. And then, as you said, we could do estimation for different estimands. And so conditional estimands where you're looking at the effect of factor one, conditional on the level of factor two, for instance, is something we could do. But even in that setting, you still want to account for the fact that there's non-compliers on factor one, right? That doesn't really solve that problem. Is that fair?
Yeah, I'm sort of. This is a bit of a fortune telling question, but you mentioned it in your presentation, so I think it's fair to ask, and I think it's important. One of the things that we worry about is interaction between the treatments, right? One treatment makes the other one less effective, that kind of thing. And your approach seems sort of targeted at trying to figure that out. The other problem is one treatment makes the other one less attractive, right? So, for example, do you diet and exercise at the same time? Well, maybe if you're dieting, you don't show up to the gym, or vice versa, right? If you pumping a lot of iron, you feel like you can eat all the chocolate you want, and
Sure.
so I know you mentioned that as sort of a difficult problem, and I'm curious about what you think. Is that problem likely to be solved? And if so, what's the general sort of approach you hope to take to tackle that problem?
Yeah, so that's a great question. So yeah, we are, yeah, when we're talking about interaction effects, yeah, we're mostly thinking on the outcome.
Mhm.
But as you said, sometimes there's an interaction between your assignment and your treatment uptake. And so that's exactly what we've conveniently assumed away with our
Right.
treatment exclusion restriction. And so this is, again, goes back to how do we weaken this in a way that makes sense? And I think it is trying to think about basically what kind of interactions we will allow. So as you said, kind of putting some kind of modeling assumptions or quasi-modeling assumptions on how is the effect of the assignment of factor 1 allowed to affect the uptake of factor 2?
Well, I don't see any more questions, so I am going to thank Nicole for being our presenter this week. I want to remind everyone that this presentation will be posted to our website shortly after the broadcast if you'd like to share the presentation with someone else or watch it again later. I also want to announce this is our last IMC presentation for the calendar year. However, I hope you will join us on Friday, February 5th, 2021, when we will host a talk by Andrew Eggers from the University of Chicago. Please see our website, www.methods-colloquium.com, to get more information about that upcoming talk. Nicole, thanks for being here today.
Thank you so much.
And I hope to see everyone next year.